due to the longer electron diffusion length. So you need to remember what diffusion length of a carrier mean, right? For example, electron diffusion length refers to the average distance an excess electron will diffuse before it recombine. Okay, so since Ln is larger than Lp, right, the excess electron will diffuse further, right, will diffuse a longer distance before they recombine compared to the host. Okay, so what that means is that if you orientate the structure like this, where the P is placed near to the surface than the N. So maybe I can go back to this diagram. All right. So if we place the P region near the surface of the LED like this, so under forward bias, when the electrons get injected into the P, they can diffuse nearer to the surface. So as they recombine, all right, the light will have a higher chance of escaping to become the useful light output. Okay, right now, if we do it the other way around, that means if we use a P plus N, all right, so now let's invert the two layers. So in other words, now this layer become N and this layer become P plus, all right, but because holes have much shorter diffusion length, so they will not be able to diffuse near the surface, okay, before they recombine. So the light emission from a P plus N junction would tend to have a lesser chance of escaping to become the useful output. Okay, so that is the reason why an N plus P structure is preferred for LED application. Okay, right. And of course, the reason for making the N side dope more heavily than the P is quite obvious. Now, if the N side can be doped more heavily than the P, then under a given forward bias, then a lot of electrons can get injected into the P. Okay, so that can further enhance the light emission from the LED. All right, so this is an important practical consideration, right? So during the operation of the LED, we would like to have the recombination events to take place near the surface so that the photons or light emitted, they have a greater chance of escaping out of the semiconductor to become the useful output. Okay, now at this point, just a reminder that not all recombination are radiative. Only direct recombination is radiative. All right, indirect recombination, in other words, recombination that occurs through defect states, are usually non-radiative. And also there is another kind of recombination which we briefly discussed last week. This is the OJ recombination. All right, OJ recombination is also non-radiative. All right, you may recall why it is non-radiative, because the energy difference is passed to a third carrier. The third carrier can be electron or hole, and making the third carrier energetic. And eventually, the third energetic carrier would actually lose the excess energy through thermalization. Okay, so the energy is not emitted through, through light emission, but it is emitted through heat. Okay, during OJ recombination. Now, OJ recombination, since it involves three carriers, right, it would likely happen under high carrier concentration condition, such as very strongly forward biased PN junction, whereby you have lots of electron injecting from N into the P. So you got lots of electron in the P. All right, so under this condition, OJ would have a high chance of happening. Okay, so there is one consideration: the structure and the doping profile of the LED. Okay, and how the two layers are placed, right? So the P region is usually placed at the top, and the N plus below. Okay. Now, although one can maximize the radiative recombination processes, in other words, we try to make as many recombination radiative as possible. The external quantum efficiency, I will come to this term later on. External quantum efficiency is actually a parameter used to measure the fraction of light that can successfully escape to become the useful output. Okay, so even though we try to maximize radiative recombination, the external quantum efficiency, in other words, the fraction of light that escape to become the visible light that we see from the LED, is actually still very small. Okay, it's usually only a few % of the number of recombination events that emit light. Okay, this problem is actually caused by this phenomenon called the total internal reflection, all right, which typically happens when light tries to travel from a denser medium to a less dense medium, such as in the case of semiconductor to air. Okay, so what is refraction? Okay, total internal reflection is actually a result of refraction. Remember, during refraction, the two angles, the angle of incidence and the angle of refraction, they are related by Snell's law. Okay, so Snell's law states that n1 sine theta 1, where theta 1 is the angle of incidence, and n1 is the angle of, n1 is the refractive index of medium 1. Okay, now theta 2 is the refractive, theta 2 is the angle of refraction, and n2 is the refractive index of medium 2. All right, this is Snell's law. Okay, now imagine a light traveling from semiconductor to air. Now, as you know, a semiconductor is obviously a denser medium, so the refractive index is higher than that of air, which typically has a refractive index of 1. Okay, so going by Snell's law equation here, so N1 for semiconductor is larger than N2. Okay, so in order for Snell's law to apply, theta 2, the angle of refraction, must be bigger than theta 1, the angle of incidence. Okay, so what that means is that when a light ray, for example, shown here by the dashed line here, tries to travel from the semiconductor to air, you will tend to diverge even further because the angle of refraction, right, is larger than the angle of incidence. So there will be a point in time where the angle of incidence becomes large enough such that the angle of refraction is 90 degrees. Okay, at this point, the angle of incidence is called the critical angle. You look at number 2 here. So when the angle of incidence becomes sufficiently large, the angle of refraction will become 90 degrees. Now, at this stage where the angle of incidence is large enough to make the angle of refraction 90 degrees, this angle of incidence is called the critical angle. Now, for angle of incidence greater than the critical angle, the light ray would not be able to escape from the semiconductor, right? Instead, it will suffer total internal reflection because now the theta 2 is supposed to be bigger than 90. Okay, so the light will not be able to escape into air. Okay, so it is due to this problem that even though we can have many recombination events emitting light within the semiconductor, only a fraction of the light can successfully escape to become useful output. Later on, we will calculate this fraction. You'll be surprised to see that it is pretty low. Okay. All right, so that basically explains the problem that engineers face when they try to design an efficient LED. All right, so there are several considerations, just a summary. So one would prefer a N plus P LED or a N plus P diode, all right, due to the longer electron diffusion length compared to the holes, okay. Then we, of course, need to fabricate this diode N plus P diode using a direct bandgap semiconductor where most of the recombination events are radiative. And of course, we would like to have a very pure direct bandgap semiconductor to minimize the defect states so as to minimize the non-radiative recombination. Okay. Now, even if we do all this to make the LEDs itself as perfect as possible, all right, there is still this challenge of getting light out of the semiconductor due to the total internal reflection phenomenon. Okay. Now, because of total internal reflection, only light generated and making an angle of incidence within a cone of 2 theta c will be able to emit from the semiconductor to become the useful light output. Okay, you can easily see this from this picture. So if the light makes an angle of incidence greater than the critical angle, then it will be reflected back. It cannot escape. So only light which are contained within a cone whose angle is 2 theta c will be able to escape into air. Okay. Now theta c can be quite small. All right. Later I will show you one example. Okay. Now not only total internal reflection is a problem. Don't forget, as light travels from one medium to another medium, it also undergoes Fresnel reflection. In other words, even if the angle of incidence is 0, in other words, the light actually is hitting the semiconductor air interface at 90 degrees. Okay, not all the light can pass through. I mean, can pass from the semiconductor to air, right? A fraction of it will still be reflected back, and this is due to Fresnel reflection. Okay. Now, yeah, actually, there is a calculation here trying to show you the value for theta c for gallium arsenide. Right. For gallium arsenide, the refractive index is 3.6. For air is 1. So if you go by these two values and apply Snell's law, you can easily calculate theta c to be around 16 degrees. Okay. Now, so only light within the cone of 2 theta c can escape into air. 2 theta c will be about 32 degrees. Now, the light emitted from the recombination events are randomly directed in all different directions. Okay, so you can expect light to be emitted in all 360-degree directions. Okay, so only 10% or less of the light emitted due to the recombination events can successfully escape into air to become the useful output. And this problem is further worsened by Fresnel reflection. Don't forget, there is still Fresnel reflection, which further reduces the percentage of light that can escape into air. Okay. Now, it can be shown that the external quantum efficiency, typically represented by the letter F, okay, can be expressed like this, where N1 is the refractive index of semiconductor, and N2 is the refractive index of, hang on, let me see, N1 and 2. Yes, N2 is a refractive index of air, and N1 is a refractive index of the semiconductor. Now, I won't show it here for today because we are going to do this derivation during the tutorial. Okay, so in order to derive this expression, we need to consider two things, right? One is the Fresnel reflection, and the other one is total internal reflection. Okay. Now, F typically is only a few percent. Okay. Later, some calculation will show that. So, in the design of LED, we need to think of ways to increase F, so as to increase the amount of light that can be transmitted into air to become the useful output. Right. So one way is to shape the semiconductor into a hemisphere. Okay. So the picture is on the next slide. So imagine this is the PN junction, and as you know, for a LED, the P is normally placed on top of the N. Okay, so one way to maximize the transmission of light into air is to shape this P region into a hemisphere like this. All right, it's quite easy to understand how that helps. Essentially, when you shape the light, when you shape the P region into a hemisphere, then that minimizes the angle of incidence that the light makes with the surface of the P region here. Okay, right. So with that, then the light can be more readily transmitted into air. Okay, so there is one approach. But however, this approach, although theoretically possible, but practically is difficult to implement because we have to grind the semiconductor into a hemisphere like this, and that takes quite a bit of effort to do that, right? And also during the grinding, you create a lot of defects at the surface of the semiconductor, so that kind of reduces the number of radiative recombination, right? And of course, it's costly because of the additional step needed to shape the semiconductor. So the second approach is more preferred. What people normally do is that they enclose the PN junction in a plastic compound. All right, so this plastic compound is semi-transparent, right? It has a higher refractive index than air, typically about 1 point something to 2. Okay, and at the same time, the plastic compound can be shaped into a hemisphere like this. All right, it's easier to mold a plastic than to grind a semiconductor, which is a very hard object, right? So to mold a plastic is very easy. So it can be molded like this into a hemisphere, and the shape itself facilitates the escape of the light from the LED into the air. Okay, so the second approach is usually preferred. Now let's try to do a comparison to how the plastic material can actually improve the external quantum efficiency. So if there is no plastic material between the semiconductor and air, then based on the earlier calculation, right, the critical angle is very small. It's only about 16 degrees. And if you substitute N1, N2 into the external quantum efficiency expression, or the expression for F, it turns out to be only 1.3%. Okay, so it's a very small number. Now, if we interface the semiconductor and air by a plastic material, so now a plastic material exists in between the semiconductor and the air, and assuming that the plastic material has a refractive index of 1.5, right, the external quantum efficiency can be increased to 0.036. It is still small. Now, this calculation or this expression in equation 7 is derived not based on a hemispherical structure like this. It's based on the flat surface. Okay, all right, so this is important to note. So to derive this, we did not assume a hemispherical surface. Okay, so assuming a flat semiconductor surface, right, even after putting the plastic material, F is still relatively small, but nonetheless, compared to the case without the plastic material, it is 3 times higher. Okay, it's about a factor of 3 higher. Okay, so by shaping the plastic compound into a hemisphere like this, the value of F, or the external quantum efficiency, can be further increased significantly. Right, because we minimize the angle of incidence using a hemisphere or hemispherical shape like this. Okay. And another consideration is that the plastic package or the plastic compound used to enclose the LED is normally kept quite thin as possible, or as small as possible, to minimize any loss of light due to absorption. Okay, so some plastic can also absorb light, so that is another important consideration. Okay. Okay, let's continue. So let's go through one example and try to have a feel of the numbers. So here we are trying to calculate the fraction of photons. They are reflected when light is incident normally from gallium arsenide at the surface or at the interface with air. Okay, so this is to calculate the reflectivity, right, due to Fresnel reflection. Also calculate the incident angle for total internal reflection. How would the result change if light was transmitted into glass and then into air instead of, in the earlier case, directly from semiconductor into air, right? Taking the refractive index of glass to be 1.5. So reflectivity is computed like this, is defined as N1 minus N2 over N1 plus N2 square. Okay, right? So it works out to be about 33%. So in other words, even though the light is directed perpendicularly at the interface between the semiconductor and the air, only 60%. Sorry, only 66% or 2/3 of it can escape from the semiconductor. The rest, 33%, all right, of the light is reflected back. Okay.
Hello, Prof.
Yeah.
Is it possible for you to accept the recording? Because it stopped just now.
Huh? Oh, it stops, is it?
Yeah.
And I'll go back.
Thank you.
I think I can start it myself. I presume it is recording. I have started it, so yeah.
Thank you.
All right, so let's go back. Sorry, I was in full screen mode, so I didn't realize there is a message here. So what is the message? Okay, all right. So that is done. Okay, right. So that is the Fresnel reflection part. Then we need to consider the issue of total internal reflection. Okay, so let's try to calculate the critical angle and see how small it is, right? It's only 16% for gallium arsenide. Right, for most semiconductor, the refractive indices are in this range, about 3 to 4. Okay, so the critical angle is typically less than 20 degrees. All right, now, if light were to be transmitted into glass first and then air, okay, so let's see how much light can pass into glass from the semiconductor. If you now take N1 to be the refractive index of semiconductor, N2 now is a refractive index of glass, which is 1.5. Okay, so the reflectivity now becomes much lower, is 18%. So it drops by half, almost roughly half. Okay, all right. So more light can be transmitted into glass. And if you check the critical angle, right, for the interface between the semiconductor and glass, this critical angle is much bigger, right? Instead of 16 degrees, it's about 24 degrees. So 24 degrees, okay? Right, so with a larger critical angle, more light can escape from the semiconductor into glass. Now you can do a similar calculation between glass and air to further see the advantage that the glass brings in this particular case. Okay. So overall, right, if we insert additional medium between the semiconductor and air, right, we can enhance the transmission of light from the LED into air. Okay. Now, during the discussion on LED in books or in papers, sometimes you will come across a parameter called injection efficiency. Okay, so this is an important parameter for LED. So how is injection efficiency defined? Right, so let's briefly discuss this. Now, as you know, an LED is a forward bias PN junction which emits light due to the injection of electrons and holes across the space charge region. So in a forward bias PN junction, right, there are two diffusion current components, right? One due to the minority electrons in the quasi-neutral P region, and the other is due to the minority holes in the quasi-neutral N region. Okay, so earlier on during the discussion on PN junction theory, we had derived the expression, the current expression. Now, what you see in equation 8 and 9 are the current density equation for electron current, for electron diffusion current, and hole diffusion current evaluated at the edge of the depletion region. Okay, right? Remember the diffusion currents are a function of distance. Okay, so the distance part is not in these two equations because these two expressions are evaluated at the depletion edges, right, where the value of x prime or x double prime is 0. Okay, so how is injection efficiency defined? Injection efficiency is defined by Jn over the total. Jn plus Jp, if you recall, gives us the total diode current. Okay. So if you have an N plus P junction, we will expect Jn to be much bigger than Jp, and thus the injection efficiency would approach 1. 1 is a maximum value. Okay. All right. So injection efficiency is a parameter used to describe how much current in a forward bias LED is carried by the electrons, essentially. All right, because of the advantage of electrons over the holes in terms of the longer diffusion length of the former carriers, right? So electrons can diffuse over a longer distance before they recombine. So that brings two benefits. One is that we can bring the light emission region closer to the surface, and light emission can happen over a broader region in the quasi-neutral P region, right? Since the electron can diffuse over a longer distance during recombination. Okay, right? So injection efficiency, typically we want the injection efficiency to be as close as possible to 1. All right. Okay, so let's go through another example. So you're asked to consider a gallium arsenide LED with the following parameters at 300 Kelvin. The electron diffusion coefficient is given. Hole diffusion coefficient is also given. Notice the big difference, all right, because the electron mobility is much bigger than the hole mobility. The p-side doping is given. The n-side doping is much higher, at least 10 times or more. Electron minority carrier lifetime, hole minority carrier lifetime, they can be comparable. Okay, and given Ni is 2 times 10 to the power 6 for gallium arsenide, calculate the injection efficiency of the LED. Okay, so for this case, we need to calculate Jn and Jp, right? As you saw earlier, that's how injection efficiency is defined. In order to calculate Jn and Jp, you need to compute some of the parameters, right? Like Dn, Ln, and Np0, and Dp, Lp, and Pn0. Now, these two terms are not important because they will cancel out when you take the ratio of Jn over Jn plus Jp. Okay, so here the calculation shows you the Np0 and Pn0 calculation, basically. Okay, by now you should know how to evaluate Np0 and Pn0, right, using law of mass action and assuming complete ionization of all the dopant atoms. Okay. Now, these two lines show you the calculation for Ln and Lp. All right. So if you compare Ln and Lp, you see that Ln is much longer than Lp, right, by a factor of 5. Okay, all right. So how to calculate Jn and Jp? Just take the ratio, right? Jn over Jm plus Jp. Now the voltage term is no longer relevant because they will cancel out each other. Okay, so for this example, the injection efficiency is about 97.8%. Not very high, right? Typically for a good LED, we would expect it to be around 99%. And that is usually done by further increasing the doping concentration of the N side over the P side. All right, so with that, we make Jn to become even larger than Jp. So that will push the injection efficiency towards 1. Okay. All right, so this will be the discussion on LED. Now, before I end this topic, I think I mentioned something earlier. Although the examples that we see here involve compound semiconductor with 2 elements like this, for visible light LED, if you look back at some of the examples I showed you earlier, for visible light LED, normally the compound semiconductor involves 3 elements. Gallium, in this example, is gallium, indium, and nitrogen. Okay, now, why is that the case? Okay, to understand this, let's go and calculate the wavelength of light emitted from gallium arsenide. As you know, gallium arsenide has a band gap of about 1.4 eV. Right, so what is the photon energy? Or rather, I mean, the photon energy of light emitted from gallium arsenide will be 1.4 eV, right? So what is the wavelength? So to calculate the wavelength, you take 1240 divided by 1.4. So the wavelength of the light coming from gallium arsenide LED will be 885, or about 886 nanometer. Now, 886 nanometer is in the infrared part of the electromagnetic spectrum. So that means if we make a LED using gallium arsenide, we can't see the light. It's infrared, right? So gallium arsenide LED is typically used for remote control, right? Those remote control for your TV, for your aircon, right? They operate with a wavelength in the infrared part of the electromagnetic spectrum. Okay, all right. Now, for visible light, such as the red color light, for example, okay, how do we achieve the red color light? Okay, so just now we calculated the wavelength of gallium arsenide LED to be about 885. Okay, now red light has a wavelength of about 700 nanometer, right? About 675 to 700 nanometer. So it has a shorter wavelength. Okay, it has a shorter wavelength. In other words, the photon energy is actually higher or lower. The photon energy is actually higher. Okay, right. So in order to achieve red light, what people normally do is that they add an additional element, a third element to gallium arsenide, which typically is aluminum. Right, typically is aluminum. And how does that lead to a larger photon energy? Right. Basically, the addition of aluminum to gallium arsenide will increase the band gap of gallium arsenide. And how does it work? Well, we have learned this already in part 1. Remember, very briefly, you learned about this in part 1, where the band gap energy of a semiconductor is dependent on the interatomic spacing. Right? So when the interatomic spacing is increased, the band gap decreases. And on the other hand, if the interatomic spacing is reduced, that means the atoms move closer to one another, right? Then the band gap can be increased. Now, aluminum is a smaller atom than gallium. By the way, aluminum is also in group 3, right? The same group as gallium. Right. So when you add aluminum into gallium arsenide, some of the gallium atom will be replaced by aluminum. Right, and that kind of reduces the interatomic distance between the atom due to the smaller aluminum atom. Okay, all right. So with that, the band gap increases. So with a larger band gap, the wavelength can be reduced, and then into the visible light spectrum. Okay, right. So that is the basic idea why in LED application, typically a LED for visible light application, it involves 3 semiconductor. Now, the same explanation can be applied to this example of gallium indium nitride. Okay, now gallium nitride is a semiconductor, is a compound semiconductor with a band gap of 3.3 eV. Okay, so if you calculate the wavelength of the light coming out of a gallium nitride LED, it's about 375 nanometer. Right, 375 nanometer is in the UV part of the electromagnetic spectrum. So an LED made using gallium nitride does not emit visible light. Okay, so in order to make blue light come out from gallium arsenide, people introduce indium, okay, into the gallium nitride crystal. So when indium replaces gallium, okay, if you check the atomic radius of indium is bigger than that of gallium. All right, indium is a bigger atom. Okay, so if you put indium into the crystal lattice of gallium nitride, the interatomic spacing is increased. All right, so with larger interatomic spacing, then the band gap decreases. So with a reduction in the band gap, then the wavelength increases. So by adding indium into gallium arsenide, we can make the LED emit blue light or green light, depending on the composition of indium. Okay. So that's how people tune the colors of LED, is through the addition of a third element to the compound semiconductor. Okay. The 2 examples that I give you involve an element that tried to replace gallium. Okay, so there is another example that you saw here, and this is on this one, right? Gallium arsenide phosphorus. So in this case, the third element added to gallium arsenide crystal is phosphorus. All right, so instead of adding an element from group 3 to replace the gallium, we can also add an element from group 5 to replace the arsenic. Okay, so it's the same idea essentially. So this semiconductor can produce orange light, red to orange, all right, similar to aluminum gallium arsenide. Okay, all right, so that's the basic idea in the choice of material, depending on the color of the light that you wish to have. Okay, so with that, the discussion on LED is complete. I think I can allow some time for questions. Next topic that we're going to move on will be on junction photodetector. Any question? Okay, if you have no question, then I think it's a good time to go for a break. All right, before we begin the discussion on photodetector. So now the time is 5:05. All right. So let's go for a 15-minute break. So please join the discussion again at 5:20. right? All right, guys, welcome back. Let's continue the discussion. We only have one more topic remaining, and this is on junction photodetector. So what is a junction photodetector? A junction photodetector is a PN junction operated under reverse bias condition, which converts light energy into electrical energy. Now, junction photodetectors are used in many applications. One classic example is digital camera. Now, I'm sure you own a mobile phone. Each of you own a mobile phone, right? There's a camera. There's a digital camera on the mobile phone. For example, the camera can have a resolution of 8 megapixel. Okay, so what does that mean? That means there are 8 million pixels, right, in the digital camera, and each pixel typically corresponds to a group of 4 photodetector for a color camera. If you look at the black and white camera, it's much simpler, right? If you have an 8 megapixel black and white camera, essentially each pixel corresponds to 1 photodetector or 1 PN junction. Okay, so in a digital camera, the photodetectors are arranged in an array, in a 2-dimensional array, corresponding to the 2-dimensional pictures that you take using the camera. Okay. All right, so that's the whole idea of a photodetector. It detects light, and it can measure the intensity of the light it detects by converting it into an electrical signal. Now, in lab 3, in fact, you will be using a junction photodetector. It is actually attached to the monochromator. All right. For those of you who have done lab 3, you probably know what I'm talking about. Essentially, a monochromator is a light filter that allows light of a particular wavelength to pass through. So after the light has passed through the monochromator, essentially we want to measure the intensity of the light or the brightness of the light that has passed through the monochromator. All right, so to do that, we need to convert the light back into electrical signal, and this is done through the use of a photodetector. Now, a typical example of a photodetector is shown in the diagram here, like this. All right, the tin can encloses the photodetector, which is inside here at this part of the picture here. Okay, there is a window, a glass window. So the purpose of the glass window is quite obvious. It allows light to pass through, and therefore the light can reach the photodetector. Now, in most photodetector, there is usually an amplifier attached to the PN junction. So if you look at the circuit diagram shown here, all right, this is the photodetector. It has a diode symbol similar to a normal PN junction, right? And there are 2 additional symbols here denoting the light rays, right, approaching the PN junction. Okay. So the output from this photodetector is connected to an amplifier. This is an amplifier. All right. Now, the purpose of the amplifier is actually to boost the electrical signal from the photodetector, which typically is quite weak. All right. So we need an amplifier to further amplify it before it can be used for other purposes. Okay. Now, how does the junction photodetector work? This is what we are going to discuss. In fact, any semiconductor, you don't need a PN junction. Any semiconductor, N-type or P-type, can function as a photodetector. In fact, we studied this in part 1, right? I think under the chapter on non-equilibrium, where there was a discussion on optical illumination applied to a semiconductor. So when light shines on a semiconductor, and if the photon energy is at least equal or bigger than the band gap energy of the semiconductor, then the photons can be absorbed, right? And the absorption of the photon leads to the creation of electron hole pairs. So what that means is that when light shines on the semiconductor, additional excess electron hole pairs are being created. So if we bias a voltage across the semiconductor, we will get an additional current flow due to the excess carriers generated by light. Now, these excess carriers generated by light are typically known as photocarriers, right? Photocarriers. Okay. So essentially, light can increase the conductivity of the semiconductor, and from there we can use this special property of the semiconductor to detect light, right? Now, a PN junction can enhance the light detection performance. Okay, so we are going to discuss how that can happen, right? Next. So how does the junction photodetector work? Okay, why do we need a PN junction? That is the main question that we're trying to understand. Okay, now if you have only a normal semiconductor doped either P or N, so imagine there is no PN junction here, there is only a P doped semiconductor here. All right, so if you shine light on the P-type semiconductor, electron hole pairs can be created, and if you connect a circuit like this, all right, so electrical current can be registered, right? Well, essentially more current can be registered when light is present due to the excess electron hole pairs created. Now, in a normal semiconductor, the excess electron hole pairs, after being created, they can readily recombine again. Okay, so when the excess electrons and holes recombine, the effect of the light is lost, or the light can be severely underestimated due to the recombination of the electron hole pairs. All right, so that makes a normal semiconductor quite a poor detector of light. It can detect light, but its performance is not very good. Now, how does a PN junction enhance the performance of the light detection process? Now, in the PN junction, we know that there is an electric field in the space charge region. Okay, so when light shines onto the semiconductor, especially when light enters the space charge region of the PN junction, right, electron hole pairs are similarly created, but due to the presence of the electric field, the electron hole pairs created can be separated, right? They are separated by the electric field. So if the electron hole pairs are separated by the electric field, then the tendency of them recombining will be reduced. So this is how a junction photodetector can enhance the light detection capability. Right? It's as simple as that, nothing complicated. Okay. So what you see below here is the energy band diagram of this PN junction. Right? Under reverse bias, I will let you know why reverse bias is essential. But essentially, there is an electric field, right? So if you imagine a photon is being absorbed, and an electron hole pair is created. So the electric field in the space charge region can separate the electron. So the electron will be attracted towards the N side, all right? And the holes will be attracted towards the P side. Okay, so this separation of the electron hole pairs would minimize the recombination and therefore minimize the loss of the photocarriers. Okay. So a PN junction photodetector is actually more sensitive than a normal semiconductor photodetector. Okay, so of course, when the electrons and holes are separated, they can flow as additional current outside the circuit to register the presence of the light. So this is a circuit symbol for a photodetector. It has the normal PN junction diode symbol with additional arrows representing the light rays. Now, this is a typical cross-section of PN junction photodetector. It's quite similar to the structure of a LED. Right? Although there is no preference as to whether we need to have a P plus N or N plus P. Both can work equally well. Okay, in the case of photodetector, P plus N or N plus P both work equally well. Okay, so there's an opening at the top of the structure here. Right, so this opening is to allow light to enter the PN junction. Okay, so on top here, there is usually an anti-reflection coating layer shown by the green region here, anti-reflection coating. Now, the whole idea is to minimize the reflection of the light. Now, as you know, Fresnel reflection will only allow a certain percentage of the light to enter the semiconductor. And to minimize Fresnel reflection, an anti-reflection coating is normally placed at the top here. So that will enhance the transmission of light from air into the semiconductor. Okay. Now, a junction photodetector can be made using any semiconductor, not necessarily to have a direct bandgap semiconductor. We can also make a junction photodetector using an indirect bandgap semiconductor. Because there's no emission of light involved, rather there is only absorption of light involved. So both types of band gaps are suitable.
Hi, Prof. Sorry. For the you just the P side, how does the recombination affect the conductivity again? Like why is it not sensitive enough?
Okay. Let me adjust my mic. Okay, so imagine we do not have a PN junction. We just have either a P-type or N-type semiconductor. There's no PN junction here. All right. Okay, so when light shines onto a normal semiconductor, electron hole pairs are similarly created. Okay, but because the electric field generally is not that strong in a normal semiconductor, the electron hole pairs will tend to recombine. Right, so that recombination results in a loss of photocarriers. So the detection capability of a normal semiconductor is not as good as a PN junction. Now, if you recall, in the depletion region of a PN junction, there is a very large electric field. All right, we did some calculations previously in some of the tutorial questions, whereby you calculated the maximum electric field at thermal equilibrium. Right, the maximum electric field at thermal equilibrium is typically on the order of 10 to the power 4 volt per centimeter. Okay, 10 to the power 4 volt per centimeter. So this is a very large electric field which can efficiently separate the electrons and holes when they are created. So the separation will minimize the carriers will prevent the carriers from recombining. Right, minimize a recombination, and therefore it minimizes the loss of the photocarriers. Okay, so a junction photodetector is more sensitive to light than a normal semiconductor photodetector. Right, now the key lies with the strength of the electric field. Okay, you can easily calculate, if you want to achieve 10 to the power 4 volt per centimeter electric field for a normal semiconductor, imagine how large the voltage you need to apply. Okay, so from this point of view, junction photodetector has a much better performance compared to a normal semiconductor photodetector.
Okay, I see. Thank you, Prof.
Okay, so in summary, a junction photodetector is basically only a PN junction. It's operated in the reverse bias mode, right? I mentioned this just now. How about forward bias? Can forward bias work as well? We will discuss this in a moment. So a junction photodetector essentially converts light via absorption process into electrical charges through the generation of electron hole pairs. All right, and Typically, this happens within the space charge region. All right. The electron hole pairs preferentially should be generated within the space charge region. All right. For electron hole pairs generated outside the space charge region, they will be lost through recombination, because the electric field outside the space charge region is much weaker than the electric field within the space charge region. Okay. Okay, why reverse bias? So that's the next question we want to understand. Well, if you remember what you learned under the topic of PN junction, you will probably have guessed the right answer. Now, when we reverse bias the PN junction, the applied electric field reinforces the built-in electric field. So the total electric field becomes larger. So this is one advantage of reverse bias, right? With a larger electric field, the electron hole pairs can be more easily separated or more readily separated when they are generated. Okay, so that enhances the performance or the sensitivity of the photodetector to light through minimizing the loss of photocarriers due to recombination. Okay, so photodetectors are usually operated under reverse bias for this reason. Now there's another reason. Remember, when the PN junction is reverse bias, the depletion width extends, right? It becomes larger than the thermal equilibrium case or the forward bias case, right? So under reverse bias, we get a much wider depletion width, and that enhances the absorption of the light. That basically increases light absorption. In other words, more electron hole pairs are generated due to the wider space charge region under reverse bias. Okay, so this second reason will also make the photodetector more sensitive to light. All right, so these two reasons, because of these two reasons, a junction photodetector is usually operated under reverse bias condition. Okay, so if we have a higher electric field, which can efficiently separate the carriers once they are generated, preventing them from recombining, and if more light can be absorbed due to the wider depletion region, more photocurrent can be produced for a given light input. So that makes the photodetector more responsive. Okay. Why not forward bias? Right. So after the discussion on reverse bias, I think most of you would have guessed the reason why a junction photodetector is never operated under forward bias. Now, under forward bias, the applied electric field opposes the built-in field. So the net electric field becomes weaker. So that does not give a very good incentive to operate the photodetector, right? So with a weaker electric field, then the electron hole pairs are less efficiently separated when they are generated. Now, in addition, under forward bias, the depletion width narrows down. It becomes smaller. The depletion region becomes smaller. So less light is absorbed within the depletion region. Remember, light absorbed outside the depletion region do not generate a lot of photocarriers due to photocarriers being lost through recombination. Okay, once they are generated. Right, so under forward bias, the junction electric field becomes weaker, so the electron hole pairs are less effectively separated when they are generated. All right, and the depletion width becomes narrower. There's a third reason. Remember, under forward bias, we have carrier injection across the space charge region. And the direction of the forward bias current actually opposes the direction of the photocurrent. Okay, I might not have introduced this phrase photocurrent to you, but essentially the additional current that we get when light is present, right? Due to the electron hole pairs generated by the light, we get an additional current, and the additional current is called a photocurrent. Now, if you check the direction of the photocurrent in this diagram, okay, so the electrons generated will be swept towards the N side. The holes generated will be swept towards the P side. Okay, so essentially the photocurrent flows. If you look at the external circuit, the photocurrent will flow in a clockwise direction. In other words, it flows from the P to the N. Okay, so the photocurrent flows in the clockwise direction like this. Now, if you look at a forward bias photodetector, okay, right. So in the case of forward bias photodetector, we have electron hole pair injection across the space charge region. So in other words, holes are injected from the P side to the N side, and electrons are injected from the N side to the P side. If you check the direction of the hole and electron injection, they are opposite to the direction of the photocarriers. All right, remember the photocarriers are separated such that the electrons go to the N and the holes go to the P. But under forward bias, the holes are injected from P to N and electrons are injected from N to P. So the forward bias current actually opposes the photocurrent. So that further reduces the magnitude of the photocurrent that can be detected by the external circuit. And in most cases, if the forward bias is large enough, the forward bias current will totally overwhelm the photocurrent, making light detection almost impossible. Okay, right, under forward bias condition. Okay, so the a junction photodetector is never operated under forward bias condition. All right, because that makes the photodetector a lot less responsive to light compared to reverse bias condition. Okay. Now, the answer to the first question is probably known by now. Why only electron hole pairs generated within the depletion region are important? Because an electric field exists, a strong electric field exists in the depletion region, so that can efficiently separate the carriers, preventing them from recombining after they are generated. What about those generated outside the depletion region? Are they important to the operation of the photodetector? Do they also contribute to, do these carriers also contribute to the photocurrent? Yes, provided the photocarriers are generated within one diffusion length from the edge of the space charge region. So how to understand this statement? Okay, it's quite easy. You just need to recall. Okay, what happens under reverse bias? Maybe I will go to the next diagram first. It might become clearer. Well, let me come here first. Okay, right. Now, based on what we have learned under PN junction topic, under reverse bias, we have minority carrier extraction across the space charge region. All right, so the whole concentration in the N region here, at the edge of the space charge region will drop to 0, and that establishes a gradient in the whole concentration profile here. There's a non-zero gradient, and that drives the diffusion of holes towards the space charge region. Okay. Similarly, there is a gradient in the electron concentration profile here, which drives the diffusion of the electrons, right, from the rest of the P region towards the space charge region. Now, when you shine light onto the PN junction, basically you generate excess carriers due to absorption. So the concentration of the holes increases. Similarly, the concentration of the electron also increases. But however, due to the extraction process, right, whereby holes are extracted to the P and electrons are extracted to the N, a non-zero gradient continues to exist in the minority carrier concentration profiles. Okay, all right. So remember this. Okay, so to answer this question, whether carriers generated outside the depletion region, are they important? Do they also contribute to the photocurrent? It really depends on where they are generated. Are they generated within one diffusion length from the edge of the depletion region? If they are, then the answer is yes. These excess photocarriers can diffuse towards the edge of the depletion region, and they can be extracted by the electric field to the opposite side of the junction. Now, however, if the carriers are generated outside one diffusion length from the depletion age, for example, shown by the red color symbols here, okay? Now, this electron hole pair would likely recombine before they even have a chance to be separated. All right, so that is the answer to that question. It is important provided the photocarriers are generated within one diffusion length from the depletion ages. Okay, only these carriers can manage to diffuse towards the depletion region and get extracted to become the photocurrent. Okay. However, for carriers generated outside one diffusion length from the depletion age, they are not separated by the weak electric field, and therefore they recombine and the effect of the photon is wasted. Okay, right? Remember, there is only a weak electric field present in the quasi-neutral P and N region. However, although photocarriers generated within one diffusion length away from the depletion ages can contribute to the photocurrent, we do not want them to dominate the photocurrent. Why is that so? We will still prefer the photocurrent to be dominated by photocarriers generated within the space charge region. Okay, the reason is because the diffusion process is a very slow process compared to the drift process. Now, the drift can always be enhanced by the strength of the electric field, but the diffusion is only controlled by the concentration gradient, right? So, and you can also see the big difference between the diffusion coefficient and mobility from Einstein equation. Remember, for example, for electrons, dn over mu n is kT over q. What is kT over q at room temperature? Is 0.026. All right, so the diffusion coefficient is a small fraction of the mobility. Okay, so the diffusion process is actually a very slow process compared to the drift process. All right, now if we allow the photocurrent to be made up of photocarriers generated mostly outside the space charge region, although these carriers can contribute to the photocurrent, but because the diffusion process is slow, the response of the photodetector to a changing light signal can be compromised. In other words, photodetector can operate under fluctuating light condition. They are supposed to operate under fluctuating light condition. So if the light fluctuates too quickly, right, then the photocurrent may not be able to respond to the fluctuating light very well if most of the photocarriers are generated outside the space charge region, or the bulk of the photocurrent, right, is due to photocarriers generated outside the space charge region. Okay, because diffusion is a very slow process. Remember, all right. Okay, so to summarize, yes, electron hole pairs generated within one diffusion length from the depletion age can contribute to the photocurrent because these carriers can successfully diffuse towards the space charge region and get extracted to become the photocurrent. Okay. However, we want to minimize their contribution to the photocurrent because diffusion is a relatively slow process. If we depend on these carriers to form the photocurrent, then the photocurrent cannot change very quickly in response to a changing light signal. In other words, the response speed of the photodetector will be compromised. Okay, or in other words, we do not get a very high speed photodetector that can respond to a very rapid change in the light condition or the light intensity. Okay. All right, so this discussion will prepare us to understand the design consideration of the photodiode, which I'm going to discuss next. Now, in designing a junction photodetector, there are two guiding principles. We want to maximize photon absorption within the space charge region because these photocarriers generated within the space charge region can contribute to the photocurrent, and because they contribute to the photocurrent through the drift process, all right, the photocurrent can respond very quickly to a changing light signal. Okay, we want to minimize photon absorption in the quasi-neutral region because these photons are either wasted because the electron hole pairs generated by these photons would eventually recombine and the effect of the light is lost, or even though these photocarriers are generated within one diffusion length from the edge of the depletion region, these carriers can contribute to the photocurrent, but the photocurrent cannot respond quickly to a fast changing light signal. Okay, so when we design a junction photodetector, we want to have as large as possible a depletion region. So if you recall how we can increase the depletion width, one way is through increasing the reverse bias. All right, for a PN junction with fixed P and N side doping, all right, one way to increase the space charge region is to increase the reverse bias. All right, VR, the magnitude of the reverse bias for fixed doping concentration, right? But however, we cannot indefinitely do this because increasing the reverse bias too much will eventually lead to electrical breakdown. All right, we cannot operate a junction photodetector under electrical breakdown because the electrical breakdown, if it happens through the avalanche process, it is destructive. Right? Even if it happens through the Zener process, Zener tunneling process, the breakdown current is usually much larger than the photocurrent. So that defeats the purpose of the photodetector. Okay, all right. So, but we still want to achieve as large as possible a space charge region for a given reverse bias. And the only way to do that is through reducing the doping concentration of the P and N region. Okay, so as Na or Nd tends to 0, of course, the depletion wave will get larger and larger. Okay, but however, if you rely on a very lowly doped P and N region to form the photodetector, we cannot form good ohmic contact to the P and the N region. Okay, right? Remember under the chapter on metal semiconductor contact, we talk about ohmic contact, and one requirement to form a good ohmic contact. So what do I mean by a good ohmic contact? It is one with a low contact resistance. All right, we want to minimize the contact resistance, and to do that, we have to dope the semiconductor more heavily. Okay, but doping the semiconductor more heavily has an adverse effect on the depletion width. It makes the depletion region narrower. Okay, so what is usually done in the design of a junction photodetector is that we make the bulk of the semiconductor region lowly doped or undoped. Okay, this is where the intrinsic region comes in here. Okay, so the intrinsic region here means very, very lowly doped semiconductor region for both P and N. Okay, now at the end of the PN junction here, we dope the P and N regions heavily to facilitate the formation of good ohmic contact. Right, so most of the time, the resulting structure that we get, right, can be called the pin structure. So what does the word pin mean? That means the P side is doped heavily, the N side is doped heavily, but in between is almost intrinsic. Okay, so a photodetector, a junction photodetector usually has a pin structure. Now the letter I simply denotes intrinsic region. Okay, of course, we cannot have a perfectly pure semiconductor. Most of the time in reality, all right, the intrinsic region is a very lowly doped semiconductor region with doping concentration typically on the order of 10 to the power 13 or 10 to the power 14. All right, for the case of a silicon junction photodetector. All right. So remember how a good junction photodetector should be designed. Okay. So what are the main advantages of the PIN structure? Well, if you keep the intermediate region here as lowly doped as possible, then for a given reverse bias, we can have an additional degree of freedom to control the width of the depletion region by simply physically changing the length of the intrinsic region. Right? We do not rely entirely on the reverse bias to change the width of the space charge region. Okay, so we can fix the reverse bias at a moderate value, not too high, to prevent breakdown. And we can physically lengthen the intrinsic region to increase the width of the space charge region. All right, so this is a very important advantage of a PIN structure. Okay. Now, the second main advantage is that we can make the P plus and the N plus region very thin. All right, because they are so heavily doped. All right, they can be very thin and yet they can form very good ohmic contact with the metal. And having P plus and N plus region to be very thin helps minimize the absorption of light in the P plus and the N plus region. In other words, we maximize the absorption of light within the intrinsic region. That maximizes the photocurrent for a given light condition. Okay, right? So coming back to the diagram which I showed you earlier in the initial slide. Okay, so with that, you will understand why the why a junction photodetector has a structure that looks like this. All right, where the P plus region is usually made very thin. Okay, this is to minimize the absorption of the light within the P plus region. So less light absorbed in the P plus region means more light can be absorbed in the depletion region. Okay, all right. Now, as mentioned before, it is not necessarily to always have a P plus region at the surface here. It can be N plus as well. Right, so there's no preference between P plus N and N plus P in the case of a junction photodetector. Okay, what I have discussed earlier, right, has all been summarized in the next few slides. Okay, so you can go through the next few slides on your own as you revise this topic. Okay, now the next few slides actually tries to compare between junction photodetector and LED. Right, and at the same time, it also discusses how the junction photodetector work. Right, so basically, what happens is that an LED is a forward bias PN junction, whereas a junction photodetector is a reverse bias PN junction. Okay, and LED is a device that converts convert electrical energy into light, whereas the photodetector does the opposite. It converts light into electrical energy. Okay, so because in the case of junction photodetector, right, light is absorbed. Okay, so there is no requirement to have a direct bandgap semiconductor, and indirect bandgap semiconductor can be used, all right, for junction photodetector as well. What is most important is that we need a semiconductor with the right bandgap so that we can detect light of the right photon energy, okay, or wavelength. So just to keep that in mind. Now, the third paragraph here, right, touches on the point that we actually had discussed previously. Remember, to generate electron-hole pairs, the photon energy must be at least equal to the bandgap. But usually, we would choose the semiconductor to have a bandgap slightly smaller than the photon energy that we want to detect. Because for more energetic photons, they can create electron-hole pairs more efficiently through absorption. Or in other words, a semiconductor with a bandgap smaller than the photon energy can more readily absorb the light. All right, remember we discussed this when we talk about the absorption coefficient alpha. All right, there are two reasons why alpha is a function of the photon energy. All right. Okay, so photon incident on the detector surface are absorbed by the semiconductor. Okay, to minimize the absorption, so we need to make the P plus or the N plus region at the surface very thin as possible. All right, to allow more photon to penetrate and reach the depletion region. Okay, this point has been covered. So the junction must be reverse biased to create a high electric field that can help separate the charge efficiently once they are generated. Okay, all right, so this point has also been covered. So photocarriers generated within one diffusion length of the depletion region can contribute to the photocurrent, but in consideration of the response speed of the photodetector, it is important to minimize this contribution. Okay? Because of the rather slow diffusion process. Now, photon absorption, remember, is a strong function of wavelength or photon energy. So for short wavelength or high photon energy, the absorption coefficient alpha can become large. Now, this can pose a problem for the design of junction photodetector used to detect energetic photons. Okay, to elaborate on this, let me go back to this drawing. So imagine I want this junction photodetector to detect energetic photon. But because the alpha, the absorption coefficient, increases with the photon energy, if you recall, all right? Now, what that means is that more energetic photon will be absorbed near the surface region compared to the case when the photons are less energetic. So what that means is that in the case when the photons are more energetic, fewer energetic photons will penetrate the P plus region and go into the space charge region. So that can lead to a reduction in the photocurrent. Okay, so this can be a problem. This can be a challenge in the design of junction photodetector because there is no way we can continue to make the P plus region thinner and thinner and thinner. All right, so there is a physical limit as to how thin the P plus region can be. All right, so this is a challenge that people are still trying to resolve currently. How to make the junction photodetector more efficient for detecting photon of higher energy. Okay. Now, in the same context, a junction photodetector has a different sensitivity to the red and blue light. Okay, for example, if you use the same junction photodetector to detect red light, it actually can be more efficient or more responsive than the same junction photodetector when you use it to detect blue light. Why is that the case? Because blue light has higher photon energy than red light, almost double, right? It's about 400 versus 700 nanometer in terms of wavelength, right? So blue light has almost double photon energy compared to red light. So the absorption coefficient, right, of the semiconductor for blue light is actually larger than that of red light. So if you shine blue light onto the same photodetector, a larger fraction of the blue light can be absorbed within the P plus region and become wasted. Or in other words, a lesser percentage can actually penetrate and go into the space charge region. Okay, so let's keep that in mind. Yep, to reinforce that, so this paragraph is actually emphasizing the same point. So to detect short wavelength or more energetic photon, we need detectors with junction very close to the silicon surface. All right, so the P plus region should be made very thin, but there's a physical limit how thin that can be. Okay, all right.
Hi, Prof.
Yeah.
I have a few questions regarding the just now.
Okay.
How can an electron hole in? Actually, can it be combined in the space charge region?
Okay. Remember, in the space charge region, there is a large electric field. Okay, so this diagram will be better. So within the space charge region, there is a large electric field. So that helps to separate the electron and hole pairs when they are created. So the chance of electron and hole recombination will be minimized. Although, yes, there is still a tendency, but then this probability of recombination is minimized.
I think the main reason why is because isn't the space charge region fully ionized? So, how can there be recombination even if it's fully ionized?
No. I think you are confused between ionization of dopants and recombination. Recombination can happen in a doped or undoped semiconductor. Recombination refers to an electron from the conduction band falling back and occupy an empty state, which is the hole in the valence band. This is recombination. It doesn't have anything to do with ionization of dopants. Are you referring to the ionization of dopants?
Yes.
Yeah.
Oh, okay.
They are two different things altogether. Please don't get confused, all right? Now, why is there a large electric field within the space charge region? Because of the presence of the uncompensated space charge or the ionized dopant atom. Remember, in the p-n junction theory, we have ionized donor atoms on the n side. These are the positive space charge, right? And the ionized acceptor ions on the p side give you the negative space charge. Okay, so the electric field comes from there. Of course, this electric field can be enhanced further through the application of reverse bias. Okay, so you need to be careful here. All right, so coming back to the point just now on the thin P plus region. So the P plus region should be made very thin. All right, this is important for the detection of high energy photons. All right, but of course there's a limit as to how thin you can make the P plus region. Okay. Remember, the most effective part of the junction photodetector is the space charge or the depletion region. Right, because this is when the carriers, the photocarriers can be separated efficiently to minimize the loss through recombination. Okay. All right, so I think many points have been discussed, so you can read through these few slides. Now, to make a fast photodetector, right, we need to minimize the contribution to the photocurrent from the photocarriers generated outside the space charge region, because the diffusion process is very slow. Okay. Okay, so this part has been discussed, so I won't go through it again. This part, I have already discussed it when we talk about the PIN structure just now. All right, why such a structure is preferred for junction photodetector. Okay, the next thing I want to cover is on the calculation of the photocurrent in the photodiode or the photodetector. Okay. So essentially, we need to quantify the number of photons absorbed within the space charge region. Okay, we are going to do that in detail in the tutorial. So here I will just give you a brief outline how the number of photocarriers generated within the space charge region can be computed. Remember earlier we talked about Lambert's law. Lambert's law basically quantifies the absorption of light as it travels within the semiconductor. So imagine you have a space charge region of a certain width. Maybe I can go back to a diagram like this, okay? Okay, this is not so good. Let me back to this drawing here, okay? Essentially, a photodetector has such a structure where light enters through one side of the p-n junction. Okay. So imagine you have this diagram here. So the depletion region is of a certain width. Okay. So you have light coming into the p-n junction through one end here. So how do I quantify the amount of light absorbed within the space charge region? I can use Lambert's law. All right, so after accounting for reflection, all right, I can compute the light intensity of the light after traveling past the P plus region. So I can compute using Lambert's law the light intensity at this edge of the depletion region here. I can do the same using Lambert's law to compute the light intensity, okay, at this second edge of the depletion region here. So the difference in the two light intensity will give me the amount of light energy absorbed within the space charge region. And assuming that each photon absorbed creates one electron hole pair that is not lost, right? So we have neglected recombination within the space charge region. Then I can calculate the number of electron hole pairs generated within the space charge region. Okay, GL. All right. Okay, so with that, I can compute the photocurrent. The photocurrent can be calculated like this. This based on equation 12. Right. The photocurrent can be calculated based on the number of carriers generated within the space charge region, as well as one diffusion length. If you want to also include the contribution from photocarriers generated within one diffusion length, you can do that as well. Okay, right? So GL is a number of photons absorbed within this region, which gives you, each photon absorbed gives you one electron hole pairs, multiplied by the cross-sectional area and the charge. So that will give me the photocurrent. Okay, now the total current flowing in the PN junction can be expressed by equation 11. All right, remember, not only the photocurrent flows in the PN junction, but also the usual electrical current arising from either the forward or the reverse bias. Okay, right? So that has to be accounted for as well. Now, the negative sign here is used to indicate the fact that under forward bias condition, right, the electrical current that flows in a forward bias PN junction opposes the photocurrent. So that gives you an overall smaller current than the photocurrent under forward bias. On the other hand, under reverse bias, V is negative under reverse bias. So under reverse bias, we only have the reverse saturation current flowing, which is a negative quantity. So the two negative sign will give you a plus here. So under reverse bias condition, the reverse saturation current is actually added to the photocurrent. But in most cases, the reverse saturation current is much smaller than the photocurrent. So under reverse bias condition, the photocurrent dominates. Right. So that again reinforces the point that why the photodiode or the photodetector should be operated under reverse bias condition. Okay, so we can draw an equivalent circuit diagram to represent equation 11. All right, so this is the photodiode, right? So under forward bias, I will have a diode current flowing, represented by the current ID, right? Okay, and this diode current will become, I'm sorry, for forward bias, it should be the blue color, right? So under forward bias, I have a diode current flowing. Okay, so I think I make a mistake here. Let me just double check. Oh no, it's correct. Okay, so under forward bias, I have usual electrical current flowing due to the injection of carriers across the PN junction. All right, but the photocurrent is in the opposite direction to the diode current, so the net current is actually reduced. Okay, but under reverse bias condition, the two current actually add up together. Right, this is the reverse saturation current that flows under reverse bias condition. So it adds up with the photocurrent to give you an even larger total current through the photodiode. Okay. Okay, let's go through one example and do some calculation to have a few of the values involved. So let's consider a silicon PN junction operated as a junction photodetector at a reverse bias voltage of 2 volts. Okay, so the diode area is given, the P side doping, N side doping are given. The electron diffusion coefficient and hole diffusion coefficient are given. Now, the reason why they are given is because in this calculation, we also want to consider the contribution of photocarriers from one diffusion length away, all right, in the region one diffusion length away from the two depletion ages. Okay, electron lifetime and the whole lifetime are given, and in this simple calculation, we assume that the light produces 10 to the power 22 electron hole pairs. So we didn't use, or we are not going to use Lambert's law in our calculation, assuming that has been done already, and this is the result that we get, 10 to the power 22 electron hole pairs created. Okay, so you're asked to calculate the photocurrent generated at room temperature. So let's first of all calculate the depletion width. I'm sure you know how to do that by now. From the reverse bias given and the doping concentration of the P and N side given, you can compute the depletion width W. Okay, you can also compute the Ln and Lp, the electron and hole diffusion length respectively, based on definition dN tau n and dP tau p. Okay, for the electron Ln diffusion length and the hole diffusion length Lp. Okay, now to calculate W, of course, you need to first of all calculate the built-in voltage of the PN junction. Okay, based on this equation. So this is the depletion width. Now, if you compare the depletion width to the Ln and Lp that you calculated here, right? Essentially, Ln and Lp are both much bigger than the depletion width. So in fact, this is a poorly designed junction photodetector. So in other words, most of the photocarriers contributing to the photocurrent actually come from light absorbed one diffusion length away from the depletion ages. Okay, right? So keep this in mind. So in reality, one would prefer W that is much bigger than Ln and Lp. And that can be made possible by a large reverse bias or by reducing the doping concentration of the P and N region. Okay, so the photocurrent generated in this case, after all these parameters are computed, can be calculated to be about 0.137 milliamp. Okay, so the photocurrent typically is in the order of hundreds or tens of microampere. Right, so if you compare this with the reverse saturation current, which is typically in this order of magnitude, so as you can see, IPH, the photocurrent, is much bigger than the reverse saturation current. Okay, and they are also in the same direction. So, but essentially, IPH generally dominate over I0. So that again explains why a junction photodetector should be operated under reverse bias condition. Now, you can also calculate the forward bias current for this PN junction, and you can see that under forward bias, the current can be easily larger than the photocurrent. Okay. All right, we are coming almost to the end of the discussion on junction photodetector. All right, before I wrap up the discussion, I just want to briefly go through an application example of photodiode in the medical field. There are many application examples. All right, well, one of them I already mentioned earlier. Remember the digital camera, all right, which is found in almost all mobile phones nowadays. All right, another application example that I'm going to discuss now is related to the eye, the human eye. Okay, so if you look at the next slide, so this is a schematic drawing of the human eye. Essentially, how the human eye function is that there's a lens, right? So when light passes through the lens, it can be focused and an image can be formed on the retina. Okay. Now, the problem is that as a person ages, the retina can become damaged. right? So as the retina is damaged, I mean, this is only one of the problems. Well, of course, there could be problems associated with aging coming from the lens itself, coming from the cornea and things like that. Okay, so but one of the common problem related to aging is that the retina can damage, right? Can be damaged due to age, and if the retina is damaged, then the vision can eventually be lost, right? A person can become blind when the retina is damaged, right? So what happens is that we can restore the vision by implanting, okay, a photodetector into the retinal region here, okay? So the photodetector can be connected to the optic nerve. The optic nerve essentially connects the photodetector to the brain, right, which processes the electrical signal, right, coming from the retina or coming from the photodetector. So under the normal circumstance, the retina is functioned properly. So the retina converts the light into electrical signal, which is sent through the optic nerve into the brain. Okay, but when the retina is damaged, it can no longer do that. So to restore the vision, so we can implant photodetector, right, at the damaged part of the retina, okay, to help restore the vision. So the photodetector actually does the same thing as the retina. It converts the light into electrical signal, which can then be sent down through the optic nerve to be processed by the brain. Okay, so there are some of the terms here that you might want to read through and be more familiar. Okay, such as CMOS. I'm not sure whether you have heard of this thing called CMOS. CMOS is currently the main technology used for IC fabrication. There's another term called BiCMOS, which essentially combines two kinds of transistor. Now, in the CMOS technology, we only use one kind of transistor called the metal oxide semiconductor field effect transistor. In BiCMOS, we use both kind of transistor, bipolar transistor and the metal oxide semiconductor field effect transistor. Okay, so these are the two technologies that can be used to fabricate microchip. And we can make the photos detector in the form of a microchip sensor array, which consists of many, many small photodiodes, okay, arranged in an array manner. All right, so that photodetector can be implanted into the retina to replace the damaged retina. Okay, so that's how semiconductor can play a part or contribute towards the field of medicine. Okay. This is just one example. Now, there are some terms here that describe the disease resulting from, I'm not too familiar with medical term, right? So these are some of the diseases that could result from aging or injury to the retina. Okay, so essentially these diseases damage the retina, causing a loss of vision. Okay, right. So with that, I think we come to the end of part 2. And also to the end of lecture 13. Okay, what to do in lecture 14? All right. Okay, before talking about that, now I would like to say something on test 2. Okay, test 2 will happen in about 2 weeks' time, or slightly less than 2 weeks, on 27th of April. All right. Now, in that week itself, we only have tutorial on Tuesday. So the arrangement is quite similar to the time when we had test 1. Okay, so please check your timetable carefully for that week. Now, the scope of the test will be the entire of part 2, excluding photodetector. So it'll be tested all the way from PN junction until LED. All right, excluding photodetector. But of course, in the final exam, all topics will be tested. Okay, all right, so that's the scope of test 2. Now, the format is similar to test 1. There'll be 4 questions to be answered over 1 hour. Right, so please manage your time properly. So on average, each question is about 15 minutes, including the time used to read the question. Okay, so that's about test 2. Now for the final exam, there is a change in the venue. I think in your timetable, it is indicated as NTU. I think now it is confirmed that the exam will be held in HCI. And please wait for further notification on the seating arrangement and the venue. That means the exact LT that you are supposed to go to. Okay. All right. What else? Okay. What should we do for lecture 14? All right. I intend to go through test 1. The 4 questions in test 1. I think some of you requested that. Okay. But I haven't received the question from Prof. Ng yet, but I will remind him. Okay. Now that is part of the agenda for lecture 14. Right. I'm not sure whether we can use the entire, or we need the entire 2.5 hours just to discuss 4 questions. Probably we don't need 2.5 hours to discuss 4 questions. Right, so what to do after we have finished test 1? Maybe I can go through some past year exam questions as well. Okay, right, so hopefully that will give you a better idea of the standard of the question and also to hopefully better prepare you for the final exam. All right, so with that, I will end today's class. If you have any questions, please feel free to ask.
Hi, Prof. Is there any chance for you to upload more revision material? I understand that you've uploaded the extra practice questions part 2, but any more questions for revision?
Okay, so you want more practice question? Yes, I can do that. I can upload another set of questions.
Okay, thank you, Prof.
Yeah.
Hi, Prof. Is it possible to upload the past year paper as well for history for the final exam?
Okay. Prof. Ng will eventually do that. The usual practice would be that we will upload the questions for 1 year. That means like he may upload the past year paper for 2018 or 2019. So you can have a few. So you can try out those questions and get a feel of the standard of the questions. But on my side, all right, there was a request for more practice question. I have already uploaded 1 set, so I can upload more. All right. Now, essentially, those practice questions, they also come from the past year exam or past test. Okay. So basically, it's serving the same purpose. Now, once you receive the actual past year exam paper, you can do a trial run, a time trial. That means you time yourself. I think the exam is 3 hours, right? So you can actually time yourself and see whether you can finish that paper within 3 hours.
Oh, I see. Thank you. Could I ask, when you upload the past year paper, would the solution be given for like those explanation questions?
No, we don't give the detailed solution. What we'll do is that answer keys will be given. Like for example, for the practice question, we'll give you the answer keys. Similarly, for the past year exam paper that will be uploaded nearer the exam, right? the answer keys will be given as well.
Okay, thank you.
Hi, Prof.
Yes.
For test 2, will there be a possibility of us seeing our scripts and going through the questions?
Test 2. Oh, okay. Yeah. Test 2. After test 2, we won't have any lessons, right? So what can be done is that we can schedule an online discussion for the test 2 questions as well. I will. Is it? Do the rest of you also agree to having a online session to go through the test 2 questions?
Yes, please.
Okay. So if there is no objection, maybe I should phrase my question like this. All right. Wow. Are there many of you who do not want to have an online discussion for test 2 question? So if I don't hear anything, that means I presume everyone wants to have a discussion for test 2 question. I can make an arrangement. Okay, I will send out the meeting schedule later on.
Green. Have they pin 1?
Okay. So I think the next thing you should be doing after today will be to start studying for test 2. Right, and then after that, start studying for your exam. So the exam paper will be uploaded typically about 1 week before your exam. Okay, so by then you should have revised most of the stuff and you are in a better position to actually attempt actual exam paper. So you can use that as a time trial to see whether you can manage the question within the allocated time.
Hi, Professor.
Yeah.
Will we get our result for test 1?
Yes, you will get your result, but not in the not in terms of the marks themselves, but you will be grouped into percentiles. All right, like for example, okay, so between the lowest test mark and the highest test mark, so this range of marks will be divided into 4 percentiles. Okay, so typically the lower 25, then between 25 to 50, between 50 to 75, and above 75, between 75 and 100. All right, so you'll be grouped based on your performance into percentiles. We will release the result in this manner. Okay.
So the result will be released together with all the exams, or will it be separated?
The result for the tests we can release to you before even the exam for history. But the overall result you will only get to know next year during the release of the A-level results.
Okay, thank you, Professor.
Okay, so
Hi, Prof.
yeah.
For the grading of this subject, right? Do you all grade it on a bell curve, or you all grade it on like individual merits? Like in a sense, if everybody do exceedingly well, can everybody get A, or you guys control the number of A's the history can offer?
Okay, this is a very difficult question to answer, even more difficult than the technical question itself. So, okay, just to tell you that we are not in control of how many distinctions or how many merits and so on that will eventually be given. We are not in control. MOE is the one in control, right? They will do some moderation at their side, okay? And they wouldn't tell us, right? They wouldn't say, oh, I have decided to give this number of student distinction, this number merit, and so on. No, MOE doesn't tell us. Okay. So based on historical data, so what do I mean by historical data? The data we collect by asking the student when the A-level results are released. Okay. So each year after the release of the A-level result, we will try to ask our history student how they fare. So based on the historical data that we have collected, I would say typically the distinction rate is about 30%. Okay, it's about 1/3. It's about 1/3. Now, to answer your question, the grading is definitely based on relative performance. It's not absolute performance. That's how MOE has been doing all the time for all kinds of exams. It's relative performance. Whether you're talking about O-level or A-level, I believe is all moderated and is based on relative performance over that cohort itself.
Okay, thank you, Prof.
All right, thanks.
Hi, Prof. Will we know the results of our lab, like how well we did for our lab overall?
No, I don't think we would let you know the result for the lab because the lab reports are still coming in, right? Some of you have not done the formal report for the lab 3 yet, and the due date for the formal report for lab 3 is most likely on the exam day itself, right? I mean, if you count the number of weeks from now, right? So it's typically 3 weeks after the lab. So, and you see, after test 2, we are not going to have any face-to-face lessons. So most of you cannot submit the formal report, right? So I would think most of you would only submit the formal report during the exam itself. So we cannot mark everything in time to let you know the result. Okay, so for labs, most likely we cannot release it because by then we must send the result over to MOE side already. Okay, so but I think lab you shouldn't be worrying too much. The weightage for the lab is not very high, right? I think each lab accounts for only 5%, and out of the 5%, I believe there is some percentage is allocated for the on-site Q&A. Remember, towards the end of the lab session, we will go around asking you questions. All right, so that will account for some percentage. I think 5% for both labs, and the remaining 5 is for the formal report. Okay, so I would think most of you did well. Don't worry if you cannot answer the question because those questions are meant to stretch you. Okay, so we will base the assessment on how you respond to the question, other than, right or wrong. That is not very important. Right or wrong is how you attempt or how you approach the questions themselves. Okay, that counts more than right or wrong answer.
Okay, thank you, Prof.
Now, some of you were commenting on recording. I have turned off the recording, and There seems to be something wrong with the recording. But let's see if it gets posted. It should get posted. Okay, so any more questions?
So also, Prof. Hello.
Yes.
Yeah. I joined the call my personal account a bit late because I was sharing a device with my friend in school. Like, I thought I should let you know about it.
Okay. Yes. Because that will affect the login time.
Yeah, and NTU is quite particular.
On the attendance sheet, I would take note of that.
Yeah.
Because the office will check the attendance.
Yeah.
They may ask me, but I will explain on your behalf.
Oh, okay. Thank you. Do you need me to follow up an email or?
No need. I think you have already mentioned something in the chat, right?
Yeah. Okay. Thank you, Prof.
Okay, if you have no more questions, then let's call it a day for today. And then please study hard for your upcoming test 2. Okay, so I'll see you next week during the tutorial. Okay, goodbye.
Bye, Prof.
Thank you, Prof.
Okay, bye-bye.
Thank you.